In this lesson, we're going to look at acid-base reactions. When an acid and a base react, this is known as a neutralization reaction. And when they react, we get an acid and a base reacting to form salt and water. Note that it's not just table salt or NaCl. There's a wide range of compounds that are called salts. If we look at our first reaction, we see that HCl is an acid, NaOH is a base, and it forms NaCl, which is our salt in this case, and water. Notice that water is in the pure liquid phase. This is going to be important when we look at net ionic equations for an acid-base reaction. When we look at acid-base reactions, we can predict the formula of the salt much like we predicted the potential products of a precipitation reaction. We know that the cation and anion have to be together, so that our cations are swapping anions. So H and OH come together to form water, and Na and Cl come together to form the salt. In the next reaction, HNO3 is our acid, BaOH2 is our base, BaNO32 is the salt. We see that the H and the OH form water, and the Ba and NO3 form the barium nitrate salt. Just like with the precipitation reactions, we have to re-identify the appropriate subscripts for the salt compound. Because barium has a 2+ charge and nitrate has a -1 charge, we end up with BaNO3(2). What are the products of a reaction between HNO3 and KOH? HNO3 and KOH, we're going to see that the K and the NO3 are going to come together. We need a cation and an anion. We see that they both have a +1 and -1 charge, so the formula will be KNO3. Whenever we have an acid and a base, we always get a salt, which we've determined the formula for, and then we will have water as our other product. So C and D are the correct answers. We can also identify the original reactants by knowing the products. Let's look at an example to see what solutions react to form CaCl2 and H2O. We know that the cation is going to come from the base, and the anion of the salt is going to come from the acid. Therefore, we see that we have Ca2+ and OH-, and we can figure out that the formula is CaOH2, just like we did with ionic compounds early on. And we have H+ and Cl-, and we get HCl. So the combination of HCl and CaOH2 will form CaCl2 and water. Select the acid and the base that react to form MgBr2 and H2O. We know we get Mg from the base, so we're going to have MgOH2, and we get Br from the acid, so the acid will be HBr. When we look at these neutralization reactions, we often do something called a titration, and this is a lab technique we use to identify the concentration of an unknown. So we take a known solution of known concentration with a measured volume and add it to the known volume of a solution with unknown concentration, and we add it very slowly. As a result, we're able to identify the equivalence point of the reaction, so where the moles of acid and the moles of base are equal, and we can determine the unknown concentration. When we set this up, we have what's called the titrate in the burette. A burette allows us to slowly dispense the solution of known concentration and has markings so we can measure the exact amount that was dispensed. In the flask below it is what we call the analyte. We know the volume, but we don't know the concentration. And the way we know that we're at the end of a reaction is by using an indicator. And when we have an indicator, we have a compound that is going to change structure with pH. And when it changes structure, it leads to a change in color of that particular solution. A common one we see is phenolphthalein. When we get to slightly alkaline solution, it will start to turn pink. So we know we've reached the equivalence point of the reaction. And we'll look at the calculations associated with this later on. Notice there are different indicators, and they all change color at a different pH value. And a pH is just the measure of the acidity of a solution. So depending on the substances that are the titrant and analyte, we choose the best indicator based on what we know about those solutions. A compound must change color with pH to serve as an indicator in an acid-base titration. And this statement is true. If it doesn't change color, then we have no way of knowing when we've reached that equivalence point of the reaction.